So on today's presentation, I will focus on short-haul WDM solutions, even ultra short haul, I mean over several meters, because this is also the spot when we are able to run some WDM solutions. And at the end of my presentation, I will also talk a little bit about the gray or black and white transceiver, because recently on the market there is a lot of discussion if we should go to stick to LR4, move to LR1, why to do this, why not to do this, where is the spot that we need to think about this. So I will try to show the path for the future, so then every one of us having more information could decide if it's already time to go or it's better to stay with that. At the beginning, some introduction about WDM solution, because WDM solution is the solution which is existing on the market for more than 30 years, and we have plenty of them. The most popular one is CWDM, which cover all the bands starting from O finish on the band L. But the one we'll run for the long distances is based on the C band. So it's basically called DWDM. But now, because of the operators that run enough of the frequency, because we need to put more and more data, they are looking on the two narrow bands, S band and L band. But this is what is happening for the very long distances. But we also need to keep connected the short distances. And this is something where the O band become a bit more popular, especially when we're talking about 100G connectivity, which is probably the most popular connectivity between this society here. We don't need 400G or 800G yet, or very, very rare of that, but 100G could be a very good solution for that. And some key history in the moment, which bring us where we are now with the multiplexing systems, with the wavelength division multiplexing systems. So first of all, like something new to come to the market, which is as powerful as the mouse, that we already do not think how it was developed. Every one of us is using that, or like touchable screen or printer if we want to print something for the text editor. And this for the DWDM is EDFA. So previously when we want to send anything for the long distance, we always do optical to electrical and back to optical regeneration using something what today we call transponder. That time it was basically regenerator because it only regenerates the amplitude. But now we have EDFA. So with EDFA, we go to the stage that we are amplifying the signal, the whole spectrum, not each channel separately. This brings us, of course, a bit more challenges because amplification also we amplify also the noise. That's why there was another things we developed, like forward error correction, another mechanism. This was the development which was done like 30 years ago and completely changed our way of dealing with the long-haul transmission. Then around 20 years ago, we have this big step, which was coherent modulation. Because with coherent modulation, we are able to read out of some elements from the basic system. So we are able to forget about the DCMs. Chromatic dispersion compensator, which we need to use previously if we want to have longer distances. Because coherent transceiver, dealing with that using mathematical operation inside. And the coherent revolution started at the beginning of our century, but the first deployment required a lot of computing power. A lot of computing power required big devices. So this was the reason why we have to use transponder, maxponders to do that. But today, we are able to put this computing power using the 5 nanometer, 3 nanometer, 7 nanometer lithography inside the transceiver. So in fact, our network structure could be even more simple because today, we could put the DWDM directly into router, directly into switch. We don't need all of those devices, transponders, we don't need DCM, so we need just optical layer, maxes and amplifiers, and all network will run. And this is the revolution that comes with the coherent transceiver, which are currently available in QSFP-EDD form factor for 400G speed, and QSFP28 for 100G speed. And when we talk from the cost point of view, this approach brings us a lot of savings. So first of all, when we do different comparison of services, this is the calculation per 400G ports. We see that with 400G ZR links, we occupy the less space, we use the less energy, and also the cost from the CapEx point of view is the lowest for the 400G speed. And the savings are huge. And this is some examples of the real network implementation per 100G capacity and per rack space using the different part of the networks, because saving could be different for the aggregation network, core network, or long-haul network. So this is the different savings we are able to gain using that technology. But some of you could think that that kind of technology is for the big guys because they run in the long distances, but we could also benefit with that running the shorter distances. This is the slide showing the different compatibility for QDD transceiver. And now we are moving to the shorter distances and also less speed, like 100G, few times 100G connections. So first example is the solution, very easy solution to deploy, to run the system on the distances up to 3 kilometers. The shortest DWDM system we run using that technology, we run for one customer in Poland, in the largest internet exchange point in Poland, called Plix in Warsaw. We run it between 2 floors in data center because renting the fibers in data center is pretty expensive. We know that if we need to connect 2 floors or 2 rooms, they want to charge us even like €150 per patch cord per month. So this is something which brings us huge saving because yearly cost of that patch cord will cover the cost of 100G transceiver running to that technology. So if we plan a longer investment, longer presence in that kind of network, in that kind of spot, it will be really beneficial for us because for the transceiver we pay once and we are able to use it for many years. And then we need only single fiber or dual fiber, depends how many links we need, because on single fiber, using that approach, we are able to run up to 8 times 100G channels. Or using the dual fiber, we are able to run 16 100G channels. The other approach is when we need a little bit longer distances, but we also want to keep everything passive. Because with the previous system, this multiplexer here are passive. So only what we need is fibers. And the difference between connection these patch cords from the IP devices on the both ends to our solution is that we need to be aware of the color, so then the number of the channel we are connecting. And all the infrastructure is fully passive, so we don't need to put the power supply either here for the multiplexer, either here. The example of the devices you could check on our booth. It's very easily, very simple and fully passive. So we just choose what kind of transceiver we use to adjust it to the distance we need to run. If we want to run a bit higher capacity, but still keeping the distances short, about 40, 60, 80 kilometers, we could amplify that using the amplifiers built-in transceiver as well. So using that approach, we don't need to, in fact, use extra rack space to add some amplifiers, because 2 amplifiers are built into QSFP28 form factor, and they are auto-tuning to the distance we have between them. So with this approach, we are able to run 8 or 12 channels. The channels could be colorless if we go coherent on both sides. And if we go coherent, we are able to run each wavelength even 400G. So it gives us huge capacity between 2 nodes, and we need only 2 fibers between them. Of course, if we want to make a longer distances, coherent transceiver will allow us to do that, because coherent transceiver, they have built in a lot of features, which previously was available only on the transponders. So using the sophisticated method of forward error corrections, we are able to reach the distance even 600 kilometers with 400G speeds. Having in between the sites exist in the network. And these networks, it don't need to be our networks, because we could lease alien wavelength services from the network operator and run our wavelength over that. And of course, we've run in the higher speed, like 400G links or 800G links in near future. There will be the question, but I don't have that ports in my devices because I still stick to, for example, 100G ports. So we are aware of that as well. So we could use our simple transponder, which give you also possibility to make the hybrid connection. So if, for example, in the bigger node of your network, you already equipped with 400G ports, you could install there directly 400G transceiver. But on the remote side, when you still have a device with 100G ports, you could split it to 4 times 100G on the Maxponder transponder card I show here. The only what you need to remember while setting up the infrastructure is that on those router, you need to choose the mode to create 4 times 100G port on the 400G interface, but most of the equipment support that feature. So we just select that mode instead of single 400G wavelength, and you are able to run that links. This is the other example of using that transponder, because it also helps you to build very long distance reach using Y cable and combining 2 wavelengths together to allow you to use standard transceiver. So you don't need to go to very expensive and vendor lock solution. You could use standard OpenZR Plus transceiver, reduce their speed, and with reducing the speed of those transceiver, the link length you are able to do will be much longer. I show some information here. So if we go with 800G throughput, we will be able to do 600 kilometer. If we lower the speed to 300G per transceiver, so in fact we will get the total throughput 600G, we are able to run like 1000 kilometer. But if we run each transceiver with 100G speed, we will be even able to run 4000 kilometer using only optical regeneration, so only the existing network. We don't need to go back to electrical and optical to regenerate the signal. And now what I promise you, so the things regarding the gray optics. So currently every one of us is aware that there is plenty of discussion if we should go to LR1 or stick to LR4. And what will be the impact of that decision for the future? So basically the reason of the difference in those transceiver is the modulation. The transceiver based on LR4 still using an NRZ modulation, and because they are based on NRZ modulation, we need to combine 4 wavelengths to achieve 100G. But for the FR1, LR1, and that product family, we have only single wavelength there because we use PAM4 modulation. So with the same number of light changes, we are able to carry more data. And this is something which we have to do if we want to go to the faster speeds. So basically, the FR1, LR1, this is some kind of transceiver which are getting popular now on the market. And there are a few reasons. First reason is that those transceivers are interoperable with the similar transceiver on the 400G. So on the 400G side, we also have transceiver which is called for FR1 or for LR1. And using either MPO to LC splitter, either some cassette to break out those cables, we are able to connect to single 400G ports 4 times 100G. So this is something what we will need in our networks when we will upgrade the network to 400G. Usually it will work like that we just add 400G switch on the top, and we need to connect 100G devices below. If we want to stick to LR4, in fact, we will waste 400G ports to plug their LR4 transceiver, so we will not get the higher density. And if we switch to that generation, we will be able to have the density of 100G ports using the standard 400G ports. Usually they have 32 ports on the panel, we will be able to use even 128 100G links on the pizza box. So it's very huge density. Another point to convince you to LR1 is that 800G transceivers which are coming into the market, they are also compatible with that. So it will give us future-proof solution not only for single generation, so not only for the next generation, but for next 2 generations. Because we will be able to terminate 8 times 100G on the single 800G transceiver. And another point is that we are also looking for more density even for the single ports. So now there is already one vendor who is promoting their devices with the SFP ports. So the smaller version of the transceiver which is capable of 100G transmission with SFP 112 standard. So this one will come only with LR1 because we have only 2 watts power maximum in SFP and we are not able to power up 4 lasers to gain 100G speed. So all those lead us to the point that LR1 will stay with us for quite a long time. And for breaking out the 400G and 800G, we will still use PAM4 modulation, and we have the transceiver for that. But this one used to allow us to use LC connectors. They have internally built a multiplexer with 4 CWDM wavelengths. So summing up, LR1, FR1, this is something which will be on the market, I think, quite long because will be compatible with 400G and 800G generation of the transceiver. And of course, the QSFP DD LR4 will be interoperable with the similar version of 800G, which is already on the market. And the DWDM is something what we could use not only for very long distances, but we could even benefit if we need to connect very short, even like 10, 20 meter connection also could be beneficial to use very simple DWDM solution. Thank you very much for your attention. If you have any question, please feel free.